Thanks for joining me today. In today's lesson, we are going to continue our discussion of the mathematics of chemistry and the tools that we use in that. And to start off with, I'm going to give you a scenario. And what I want you to do is, as we go through this, is think about what you would do if you were charged money for every character that you sent a text message. So let's say that you have to send this text message to a friend of yours. And we have, "Dear Bob, today while walking home from school, I got drenched in the rain. I can't believe it. My backpack wasn't zipped up all the way and my papers got soaked. I cannot read what our homework assignment for chemistry was. Can you send me the assignment? Thanks so much, Kern." So this is the text message I send out. Now, I'm an old guy, and so yes, I actually do send text messages that are full sentences because I'm old and that's what I do. But let's just say that you were going to be charged. Let's go way back in time to the old telegraph thing, and you were charged by letter. How many letters and how many characters you send is how much you were charged. Well, this sentence is 236 characters long. That is a lot of money. Let's say I'm charged 10 cents for every character. Well, then I'm looking at $23.60 to send this message. Well, I don't want to spend that much, so I want to send the same information with as few characters as possible, but I want to get all the information in there that I can. So I want you to pause the video for a second. See if you can rewrite this phrase in as few characters as you possibly can without losing any of the important meaning. I'll give you a second to do that. All right, so now that you have hopefully taken the time to actually try this yourself, this is what I came up with. Maybe you came up with something a little bit different, but this is what I came up with. Well, let's just read it. All right, we have B, walked home in rain, bag open, chem homework soaked, can't read, send please, thanks, K. Now, obviously not all the same words, but gives away pretty much all the same meaning. Now, it does require that B knows who K is and knows what I'm talking about. So that's kind of important that the person reading this has to know the shorthand. But once you know the shorthand, this is only 75 characters. That's nearly 3 times less. So instead of $23, I'm going to be spending $7. And so that is a whole lot less and a whole much better way of doing it. And that is what we're going to be talking about today. Something that we do in science to not have to write down all of the numbers that we deal with, right? In scientific notation. Scientific notation sounds really complicated, but it's really not. All it is a system for writing a very large or very small number using as few digits as possible. As few digits as possible because, well, we deal with really big numbers in chemistry. We deal with really small numbers in chemistry, in all of science, and we don't want to have to write out the 12, 13, 14, 20-something digits that a number actually is every single time we use that number and talk about that number. We don't want to write those all down. That takes way too much time and way too much effort. And so we have developed a way to only write down the important part and leave out the stuff that is not significant. And that is kind of why we deal with those significant figures previously also, is so that we only write down the stuff that is actually significant. All right? And in this system, we use powers of 10, multiplying by 10, because in our number system, a decimal system that we have, when you multiply by 10, it moves the decimal either one place to the right. If you divide by 10, it moves the decimal one place to the left. And so multiplying or dividing by 10 will move our decimal. That's why we use powers of 10 or multiples of 10 when we are doing our scientific notation. So this is what a scientific notation number looks like. This is a kind of a general form of it. We have S times 10 to the n. Well, S represents what we call the significand or the significand. Only the significant figures are used. That's why it's called the significand, because it's showing us which numbers in our big huge number written out, it's showing us which digits are significant. So we're only going to deal with the significant figures. The significand is always going to be a number that is greater than or equal to 1 but less than 10. So you're going to have 1 or 1.03 or 1.56 or 6.23 or 9.87, 9.99. It is always going to be greater than or equal to 1, but less than 10, not equal to 10. You can only have one digit and then a decimal and then other digits. That's the important thing about the significand. It's always going to be greater than or equal to 1 or less than 10. Can't be less than 1, cannot be equal to or greater than 10. And you'll see examples of how that works as we move forward. The n in our general form represents the exponent or the power of 10 that we're dealing with. It's the value of the exponent is what determines how many places the decimal must be moved to give the significand. So you're taking a number in standard notation and we're converting it into scientific notation. We're going to move the decimal. That exponent tells us how many places the decimal gets moved and which direction the decimal gets moved in order to make the significand. So if our original number, our number that we have in standard notation, is greater than 10, then our exponent is going to be a positive number. So if I have a number of like 68 billion, that's greater than 10. So I'm going to have a positive exponent. But if I have an original number that is less than 1, the exponent is going to be negative. Less than 1 would be something like 0.032. That's less than 1. It's going to be a negative exponent. Now, I want to make sure you understand these are positive. It doesn't matter whether my number is positive or negative. What matters is whether the value, the absolute value of the number is greater than 10 or less than 1. Okay? The absolute value, whether it's a positive or negative number, doesn't matter for this. If the original number is between 10 and 1 or 1 and 10, your exponent is 0. So if I have 6.3, then I'm going to have times 10 to the 0. If my original number is 6.3, then my exponent is 0, 10 to the 0. All right? Those are the three basic things of what the exponents mean. So when we're dealing with significant figures and scientific notation, you have to recognize that since the significand only shows significant figures, then when a number is given to you in scientific notation, you simply count the number of significant digits and the number of digits in the significand, and that tells you how many significant figures the number has. So if I give you a number in scientific notation and ask you how many significant figures does this number have, you just count the number of digits in the significand, because the significand shows all of the significant digits. So if it's in the significand, it is a significant digit. That's important. All right? When you're putting numbers into scientific notation, you can use that map tool that we did in the significant figures video and show you how to count how many significant figures the number has, and you use those as your significand, and then we move the decimal to get the proper scientific notation. All right, so let's do some examples so you can see what we're talking about. Many of you have probably seen scientific notation before. You've been shown this before, and this is hopefully not anything super new to you, which is why I'm going kind of fast. But if it is, then pay very close attention to what we do in these examples. Okay, so we're going to do a few examples of putting numbers from standard notation into significant or scientific notation, and then taking some numbers that are in scientific notation and bringing them out and putting them back into standard notation. So let's look at some of these examples. So let's say I have this number, 643210000 grams. I want to put this number into scientific notation. So the first thing I'm going to do is figure out what are my significant figures. So the decimal is absent, so I'm going to start over here, and I start counting over whenever I get to a number that is not 0. So I have, this is my first significant digit, and all of these are going to be significant. So I've identified all of my significant digits. Now, my decimal, even though it's not written, my decimal is understood to be right back here. Okay, we know that that's where the decimal is. So I have to move the decimal over to get me the significand. Now remember, our significand has to be a number between 1 and 10. Well, this is 64,000. if I just write that. That's 64,000. That's not between 1 and 10. So I need to move my decimal from where it is here all the way to right there. So in order to be between 1 and 10, like the significand has to be, you can never have anything more than one digit to the left of my decimal. So I just move my decimal. So here's my significand. It's 6.4321. I write down all of the significant digits. Now, I'm going to do times 10, and then I'm going to raise it to an exponent. Okay? Well, how many places did I move it? I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So my exponent is a 9. And since my original number is greater than 10, my exponent is positive. So instead of writing 643210000 grams, I'm going to write 6.4321 times 10 to the 9th. This is my scientific notation for writing that number down. Okay, let's do another example. So this time, let's say I have 9.87000 milliliters. This is my original number, and I'm told I want to put this in scientific notation. Now, I do want to point out that if you're specifically told that the number has to be written in scientific notation, then sometimes you're actually going to make the number longer or larger, or more things to write down than you would have. We're not always going to do that. Typically, I wouldn't do this with this number, but just to show you what you would do if you are told that you have to write it in scientific notation, well, I count my significant figures. My decimal is present, so I have all of these digits are going to be significant. So 1, 2, 3, 4, 5, 6. Trailing zeros are significant when the decimal is present. So all of those are significant digits. So I'm going to write down my significant digits and add times 10. Now, in order to get my significand, I didn't move my decimal at all. So that's times 10 to the 0. What this shows you is that numbers that are less than 10 or between 1 and 10, the exponent is 0 because 10 to the 0 is 1. So what this is saying, I'm taking this number and multiplying by 1, which doesn't change the number at all. All right? So sometimes writing something down in scientific notation is going to take a little bit more writing than it normally would. We typically wouldn't write this number in scientific notation. But sometimes directions of things and people will tell you that your answer has to be in scientific notation. And if that's the case, then you're going to write it like this. So let's do another example. So now, let's say we have a measurement and we get 0.000543320 grams. And I need to put this number into scientific notation. So, first thing I'm going to do is I'm going to find all of my significant figures. So the decimal is present, so I start over here, and I start counting when I reach something that's not 0. So there's 1, 2, 3, 4, 5. All of those are significant. But I have to be greater than or equal to 1. This is not greater than or equal to 1, so I have to move my decimal over to right there so that I can have 5, which is greater than 1, 0.4320. I keep that 0 because it's one of my significant digits. I keep all of my significant figures in my significand. And then I put times 10. Now, how many places did I move it? I moved it 1, 2, 3, 4 places. I moved the decimal 4 places, but my original number that I started with was less than 1. 0 point something. Anytime it's 0 point something, it's less than 1, which means my exponent is negative. So this is 5.4320 times 10 to the negative 4th grams. This would be the scientific notation for that number. Couple more examples. So let's say I have 0.0598 milliliters. Okay? So my significant figures are going to be these 3 digits only. Zeros in front are not significant. So that gives me 5.98 times 10, and I moved the decimal 2 places to get it there, and it was less than 1, so it's a -2. So 5.98 times 10 to the -2 milliliters. This is my scientific notation for that one. One last example of putting it into scientific notation. So let's say I have 1,200 kilograms. Well, my significant figures are 1, 2. So 1.2. Why do I not just write 12? Well, because 12 is bigger than 10, and my significand has to be less than 10. So it's 1.2 times 10, and the decimal's right here, so I moved it 1, 2, 3 places. 1.2 times 10 to the 3 kilograms, and that is my scientific notation. Again, putting it into scientific notation is not all that complicated, really, once you figure out how to know how many significant figures it is and where to put it. Now let's take numbers out of scientific notation. So let's say you're given the number 6.95 times 10 to the -4th liters. All right, well, this negative tells me that the number I started with is less than 1. So I'm going to move to the left. So something you need to make sure you remember, a negative exponent means decimal moves to the left when you're taking it out of scientific notation. A positive exponent means you move to the right. So I'm going to take my decimal and I'm going to move it 4 places to the left. 1, 2, 3, 4. Okay? And then I'm going to fill those in with zeros. So my answer is 0.000695. So this is the standard notation for the number that started out in scientific notation. So now let's look and see if I have 1.05 times 10 to the 5th grams. Well, 10 to the 5th is a positive exponent, so I'm going to move my decimal to the right. And so I'm going to take my decimal and I'm going to move it 5 places to the right. 1, 2, 3, 4, 5. So that gives me 105. 1, 2, 3 more zeros. Boom. Now, yes, I moved the decimal, but do I write the decimal there? No, I do not. Because if I write the decimal there, that means those zeros are significant. Because if the decimal's here, then these decimals are trailing zeros with the decimal present, they would be significant. But I don't want these zeros to be significant. I had 3 significant digits when I started. I need to end with 3 significant digits. So I do not put the decimal there. Even though I moved it, I fill in the spaces with the zeros, the placeholders, but I do not write the decimal there. So this is my standard notation for 1.05 times 10 to the 5th, written in standard notation. Now if I have 8.24 times 10 to the -3 milliliters, negative means I'm going to move to the left 3 places. So I'm going to take my decimal and I'll move it 1, 2, 3 places to the left, and that's going to give me 0.00824 milliliters. I'm simply moving the decimal the number of places that the exponent told me to and the direction the exponent is telling me to move it. All right? So here is my standard notation for the 8.24 times 10 to the -3 in scientific notation. One last example, 7.501 times 10 to the 7th grams. I want to put this into standard notation. Well, positive exponent means I'm going to move it to the right. So I'm going to take my decimal and I'll move it to the right 7 places. So 1, 2, 3, 4, 5, 6, 7. That gives me 7501, and I just moved it 3, 4, 5, 6, 7 places. And so I fill in those extra places with zeros, keeping my significant figures as they were. I still have 4 significant figures for that problem. So there is the scientific notation, putting it in scientific notation and taking it out of scientific notation. And this is not super complicated. Now, when you're rounding numbers to proper significant figures using scientific notation can be kind of complicated, because when you are doing calculations and you have to put something in proper scientific or proper significant figures, sometimes scientific notation is your only possibility. Okay, so what do I mean by that? Let's say I have a measurement, or I do a calculation with some measurements, and I get 149,500, and let's call that grams. Let's say this is my answer to my calculations. I get 149,500 grams is my answer, but I have to have only 3 significant figures because of the measurements that I used. And so I have to round this number to 3 significant figures. Well, there's 1, 2, 3 significant figures. So I look next door. That 5 means my 9 is going to get rounded up. So that's going to leave me with 150,000. So my 149,500 is going to get rounded up to 150,000. Do you see a problem with this? This number only has 2 significant figures. I need 3 because my calculation requires that I have 3 significant figures in my answer, but when I round this to my 3rd significant figure, it gives me something that's only 2 significant figures, because that 9 gets rounded to a 10, so that it becomes a 0, and without a decimal, that 0 is not significant. Well, so if I put a decimal there, that makes all of those zeros significant. That's too many. If I put a decimal there, those could no longer be significant. I could get rid of those, but that's 150, not 150,000. So I can't just add a decimal. So the only way to get 3 significant figures from this number is to put it into scientific notation. And I do that by saying, well, I need 3 significant figures. So I'm going to write 1.50. That's 3 significant figures. And in order to do that, I move the decimal 1, 2, 3, 4, 5 places. So that's 1.50 times 10 to the 5th grams. That is the only way to write 150,000 is 3 significant figures, because now everything in the significand is a significant figure. If it's in the significand, it is significant. Which also makes doing the math with scientific notation and figuring out how many significant figures is pretty easy. You just look at the significand, and however many digits are in the significand, that is how many significant figures that number has. That's the cool thing about it. But if you get to a situation where you have to round a number to more significant figures than the number has, the way you do it is you put it in scientific notation and add a 0 for all the significant figures you need. If I need 3 significant figures, I put 1 0 here. If I needed 4 significant figures, I would have 1.500. And you simply put it in scientific notation and have all the significant figures that you need, and then you do your exponents. So, hopefully you've seen the ease with which you can put things into scientific notation and take things out of scientific notation. It's not super complicated to go back and forth as long as you remember the very simple rules of your significand has to be between 1 and 10, and your exponents, if your original number is greater than 10, then your exponent is positive. If your exponent is less than 1, your exponent is negative. And if your exponent, or if your original number is between 1 and 10, your exponent is 0, because you're basically not moving the decimal at all. And you can think about the positive exponent is multiplying by 10. That's why we move the decimal to the right. Our number gets bigger. The negative exponent is dividing by 10, so we move the decimal to the left, the number gets smaller. And that is the way scientific notation works. Again, its whole purpose is to take these really big numbers that we deal with in chemistry and make them manageable numbers that we can deal with in our calculators. So I hope you enjoyed that. Thanks for watching. Have a day.